Hey guys, Satish here. This is going to be the last chapter about the basics. So there's one thing which we have left out is PCB design. PCB is the printed circuit boards. When you design a circuit, it has to be printed on a board where you can assemble your components. For R&D, you can assemble it on a general purpose PCB also. When you want to develop a circuit or a product with the circuit which you have designed, you will have to do the PCB for it. I've been doing all the simulation in Proteus, but for PCB design, I'll be using KiCad. KiCad is a open source software, so it is free of cost. So even in Proteus you can do it, but for Proteus you have to pay for it. Here it is a free software and it's pretty good at it. So let's start off with creating a new project. The power supply, if you remember the power supply which we did, the linear power supply and the SMPS power supply to convert from 220 volts to 12 volts, we will do it in KiCad. We will design a PCB for that with KiCad. So let's start with the file, new project, create a folder. Yeah, before we continue, what I'll do is for all the circuits that we have studied, that is both the power supply, SMPS and linear, then we did a few analog circuits. First one was the LDR, the second was the temperature sensor, and the last one was the high voltage and low voltage cutoff. So I will design the PCB for all of that. I'll upload the Gerber file. So if you wanted to get it printed, you can get it done. But for a single PC, it will be a bit expensive for you. So what I'll do is I'll make the board and put it on Amazon. So you can order it from there along with the component that you will need it. I'm planning to do two kits, one with all the basic equipments that you will need, that is soldering iron, a multimeter, and other thing that you will need to build the circuit. That will be one of the kits along with all the PCBs and the components required. The second kit is for the people who already have all the equipments and only want the PCB and the components. Give you Amazon link for ordering the kits. Now let's get into the PCB design. There are two aspects of a PCB design process. First one will be the schematic. Schematic is where you draw the circuit and the layout. The layout is where you're actually drawing the PCB. So let me show you an example of one of the things which I've done recently. Okay, let me take a simple one like this. This is the schematic. This is where we draw the circuit, like how we were doing it in Proteus, where we're putting in components and giving them the value. So this is the schematic part of it. The next one is the layout. That is where we actually draw the PCB. Let me open that. So it will be, you can select schematic from here and layout from here, or you can just click on this. This will be the layout where you will put footprint for individual components and wire them up. Okay, this is called as layout. So first what we will do is we will do the schematic. From here we will link each component with the footprint and make all the interconnections between the footprint. So let's open a PCB and I'll explain you what are the individual layers that it has. Let me open the graphical view of this 3D view. So this is a 3D view of the circuit that I have drawn. So the few of the important layers that is required here is the top copper layer. Top copper layer means that is the copper layer which is on the top. So the lighter green what you see here is the copper layer. Okay, so what happens, why it is useful, that is a layer which conducts. So for example, there is a resistor and LED circuit here. So this is the footprint. So we will solder a SMD resistor on top of this and a LED on top of this. From this point to this point we have to make a connection. So there will be a copper layer which will make the connection. So we basically what we tell is we draw tracks here. So now what happens is once you solder here and here, this copper track will make the connection between them. Similarly, all the interconnections are done like that. So this is the top copper layer where it will provide all the electrical connections between individual components and also provide a mounting for all the components. So this is top and this is bottom. So you can, and this is a two layer PCB. So there will be some tracks going on top and some tracks going on bottom. So why two layers? Yes, we can do it in one layer. Suppose you have a very simple circuit where all the tracks can be done in a single layer, then we will go for a single layer PCB. Suppose the circuit is very complicated and you cannot make all the interconnections in a single layer, then you will go for a multi-layer. So in this case, I am using a two-layer PCB. When we do our power supply design, you will understand that this is the top copper layer and this is the bottom copper layer. The next layer is the silk screen. So this layer is not required for the working of the circuit. It's only for the identification of the component. So this is the layer where we can write this is R18. This diode is D5. This is C3 capacitors. Without this layer, what happens is when you are assembling, you will not know which component goes where. So this is an important layer during assembly, but it is actually not required for the working of the circuit. So this is silk screen top, and similarly there will be silk screen in the bottom. So I have placed all my components on one layer, so there is no silk screen in the bottom. So it's a good practice to place all the components on one side so that it's easier to assemble. Else what they'll have to do is they'll have to assemble few components on this layer, then flip it up and assemble few components on the bottom layer. And also when they are doing machine soldering, so it's easy if all the components are on the top, else they have to solder it, flip it and send it for the soldering of the bottom layer. So that's with silk screen top and silk screen bottom. And the next layer is the solder mask layer. If you take up a PCB, you will see that it is generally green in color and few of them are blue or black. So this is that layer. So what we'll do is, for only the places where we have to solder the components, we will expose the copper, and all other places we will screen print a insulating mask. There are two advantages of it. One is it's easy to solder like that. Else what happens is once you solder at this point, the lead will flow into over the full track. So if only this area is exposed, then only the solder will stick to this. And second thing is, it gives a good kind of protection for the copper layer, else the copper layer will start getting corroded. So this layer is called solder mask top, and the bottom side will be called as solder mask 2. If you see here, the whole of this area, only all this green color thing, the tracks, everything is covered in this layer. Only the points where you have to solder is exposed. Okay, then there is an edge cut layer, that is the boundary layer, that is where they have to do the cutting. Okay, now let's start designing our first PCB. Let's open the project which we created earlier. Okay, let's start with the schematic. So this first we have to place the component. You can go here and pick the components. First let's do the power supply, that 230 or 110 volts AC to 12 or 5 volts DC power supply. So what did we do is, first is we have to provide connector to connect the 230 volts AC. So you can click, once you click on this component and click on the sheet, this will open up. So this you will need a bit of experience to select the components. What we will do here is, let's select a connector. Let's use a 2-pin male or female connector. Let's connect it here. This is where I am going to give my 230 volts AC. Now our first step, if you remember, was the 230 volts AC. We are stepping down the voltage. We were using a transformer. So now from this 230 volts input, what we have to do is, we have to connect to the primary of the transformer, and from the secondary of the transformer, that is the 15 volts AC, we have to bring it back to the PCB. I am not going to use a PCB mount transformer. I'll use a wired transformer. So this is to get the 230 volts into our board. Now we will need the same one to, so this is where I will take the 230 from the board to the transformer, and I'll use this connector to connect the secondary of the transformer back to our board. Or else what you can do is you can use a single connector and you should connect the 15 volts AC, that is the secondary of the transformer, to that point, and these two will not be required. Anyway, I'll use this so that I can show a bit more of routing. Now if you remember our circuit design, the 12 volts output from the transformer we had connected to a bridge rectifier. So I'll use 4 diodes for that. One diode, another diode. This is for a full wave rectifier. You know, this is the wire. So this point is the DC output, and this point is the DC positive, and this is the DC negative, and this is where I have to connect my AC input for the rectifier, full wave rectifiers network. Okay, after this we had okay, this is not connected. Next one what we have to place was capacitor. So you can select any component here. So I will use a polarized, so electrolytic capacitor 1, then next one was the regulator IC. Please check out the power supply design chapter before you come here, or else you will not be able to understand why I am using all these components. So we had used the 7805. We'll do both SMPS and linear. So let's start off with the linear. 7805. Then again we need another capacitor. So we need 1000 microfarad to get 1 amps of DC current after the bridge. Let me interconnect it. Then let's put a resistor and LED. We will also need a connector to take out the rectified, filtered, regulated 5 volts output. So the shortcut to copy is C. Okay, let me put the connector here. I will show you how to use off-page connectors also. Okay, now let me place a ground here. connect this point to the and connect this point to ground. Let me copy. You have to move over the component, press C, it will copy, and click here. So this connector will be my output. So let me, either you can now track the track whole way here, or else you can use a half page connector. Plus 5 volts. And R is to rotate. And for zoom in and zoom out, I am using the scroll wheel of the mouse. I'll just copy this. I can directly place it on the connector, it will make the connection. So it is good to use this connector, or else what will happen is you have to unnecessarily draw tracks everywhere. So the software will know that this and this are the same electrical point. This will also be useful when you have to make, suppose your schematic is very big that you need multiple pages. So in that case you cannot draw a track, you have to use this off page connector. Okay, now we have done this. So now, okay, now this is my 230 volts input. So what I'll do is I'll connect it to the other one from here, connect it like this. So you can either do a connection like this and connect 2 and 1 and 1 and 2, so or this. So when we get into the layout, we will do some modification so that the routing becomes easy. So this is the linear circuit. So you can mention the diode number or part number. So for this, what I'll do here is, instead of diode I'll use 1N4007. Copy this. This is a very commonly used diode for rectifier. I think the max current of this diode is 1 amps. And this capacitor, as I told you, for 1 amps load, this has to be 1000 microfarad. Sorry, 1000 microfarad, and you have to specify what is the voltage. So if you remember our power supply design channel, the voltage should be higher than the maximum voltage that you will get here. Let's assume that I am going to give 15 volts DC, then 15 into 1.5, that is the peak. So 21 volts. You should give a minimum of 21 volts. For a good design practice is to give higher voltage, or else what will happen if this voltage rating is exceeded, this diode will explode, and it will also explode if the polarity is reversed. Especially this aluminum electrolytic capacitor will explode if the polarity is reversed. So minimum is 21 volts. That is for 15 volts output. Input itself becomes, from 230 it becomes, let's say 260. Then the output also, the secondary will also increase. So it's better to have a bit higher voltage, like 35 volts or something. Check out what is the next standard value of capacitor. So let's use a 35 volts capacitor. This need not be 35 volts, because output is only going to be 5 volts. So I'll use a, let's say 100 microfarad, 16 volts, and this will be 1K. Through hole or SMD. For the linear I'll go for a through hole. For the SMPS I'll do SMD, so that you will when building the circuit you will get used to both SMD and through holes. I would initially you might think that SMDs are difficult to handle, but it is very easy to do SMD, because you don't have to cut anything, just solder it and leave it. In through hole, what will happen is you have to solder, cut, and desoldering also a problem with through hole. Is SMD desoldering is very easy. So let me assume quarter watt. You don't need quarter watt, but there is a very commonly available and used resistor. Again, go back to our LED or earlier chapters to know why I have selected 1 kilo ohm and why quarter watt. So this is the connector. So for this one, what we will do here is we will use 2 pin screw type connector and pitch. It is good to specify all the requirements of the component here itself, so that when we generate the BOM we get everything. Pitch 5 mm pitch, or 5 or 5.08. 5.08 is pretty common. You will get 5 mm. So let's assume 5.08 mm pitch. Pitch is the distance between the connector legs. There are 2 pin connectors. So what is the gap between the 2 of the pins? So you should not go very low, like 1 mm, 1.25 mm are available. But what will happen is, since the voltage that is coming here is high voltage, that is around 230 volts, it is better to go for a 2.54 mm or a 5 mm pitch. So I'll go with a 5 mm pitch, so that there will not be any breakdown or shorting between these 2 points. Let me copy this and connect it here, here, and here. So once you have made the schematic and given values to all the components, the next step is link this component to a footprint. So what you have done here is you have symbolically made a representation of all the components and interconnected them. Now how do you link it to the actual component? Like, what is the size of this diode? How many legs does it have? Whether it is a true hole or a SMD. So you have to link it to a footprint. So let's start with the connector. You can double click on it or go hover over it and press E. E is a shortcut to pull it up, and this is a footprint. Now this is not assigned to any footprint. So you have to click here. There are a lot of connectors available here. So we are looking for a this kind of connector where you can put in your wire and screw it from the top. As I mentioned earlier, we'll go for a 5 or 5.08 mm pitch, so that there won't be arcing in the bottom when we give 220 volts. So you have to search here, like you have to spend a lot of time going through all the component and see where it is. So this is available here actually, 5.08, this one. So if you click on this, you can see the 3D view of the component. So this is the component, but this is not exactly what we are looking for. It is like this one. So this is a this is like there is a base there and you have to plug in. This is like this. There is a base here and you screw it and plug it in. But this is okay. The pitch will matter. The pitch and the outer size is same to this one. So we'll go ahead using this. So you can select, double click on this, and now okay. So now you are linked this component to the footprint that we have selected. You can go through individual components here and select the footprint, or else there is a quick way of doing that. Yeah, assign PCB footprints. Here you can see first is annotate. Annotate means, see, all of them don't have a number. They're D question mark, D question mark. Once you annotate them, KiCad will assign a number based on the order of occurrence. And now this shows all the components and the footprint which you have assigned. So this is a footprint symbol, footprint assignment. So this is one what we had selected for J4. Let me copy this to all the remaining. It's a copy and paste, Control C, Control V. So now let's go for the diode IN4007. So if you come here, you might see diode, SMD and through hole. In the linear one, we will go with through hole, and in the SMPS one, let's do a SMD version. So I can click on this. If you click here, you can see all the components. So all the diodes. So this ours is. So if you know the package, you can select it here. So let's quickly see what is the DO package for 1M4007. I go to Mouser. DO 41.2. If you go DO 41, yeah. Now this is vertical cathode app. You can see the 3D view here. And a 3D view here. So this is like you want to mount it like this with the cathode or anode up. Now this is anode up, cathode up means it will be the other way. And if you want to lay it flat, you can select this. So this is pitch. Pitch is 2.54 and pitch is 7.62. So I'll show you what this is. Click on this. It has opened up here. So if you see a 3D view, now it is laying flat rather than standing up. So this is, or if you want like this, select this one. Then pitch is 10. So it is this leads are spaced wider. If you come here, this is it's more spaced, bit more wider. So we are depending on whichever you want to use, you can select. So let's go with this one only. We'll copy and paste it to the remaining. Control C, Control V. Now capacitor. Now the LED. So for LED, what you can do here is, and there are filters also here. You can type LED. So you can see all the LED. That's what you can do here is there will be LED through hole. You can go there, and this LED dia is 3 mm. So we will go to 5 mm LED. So you can again go here, click on this. It shows the footprint and a 3D view. So I'll select this. Then a resistor. You can go for resistor, search for resistor, through hole. Doesn't seem to be coming here. Okay, I have applied this filter, so let me remove this. So once you have here, so you can select which resistor you want. This is a length. You can just see the 3D view of it. This resistor 3D view is this like this, or you want to higher pitch where you want to lay it flat, go for 7. So let's see how it looks. And these are for higher wattages. So the one which we have selected is this. So let's see how it looks. So this is something which you have to spend time and explore. So this is how the through hole resistor will be on our PCB. So this is the resistor. I have selected, this has wrongly gotten selected. So for capacitor 1000 microfarad 35. First one is you have to know what is the dia of a 1000 microfarad 35 volts capacitor and 100 microfarad 16 volts capacitor. So you can just go to Mauser once again. Let's do what is the voltage? 35 volts. Aluminum electrolytic capacitor. So we'll just see what is the dia. It is 13 mm. There are multiple ones available. So let's go with this one. 10 mm. This is generally available in the market. 10 mm is the diameter and length is, the height is 25 mm. So I have to go capacitor, through hole. So axial and radial. So axial will be, let me open, it doesn't have a footprint, not selected anything. This is axial, that is leads are coming from both the ends. So if you go for a 3D view, it is like this. So this is not generally used. So we'll go for a radial. So radial 10 mm and pitch, I'll go for a 5 mm pitch. Again, if you have a capacitor, you can see which one, what is the pitch. I'll go for a 10 mm and 5 mm pitch. If you look at this capacitor like this, 3D view is this. I'm going to use a capacitor like this for this. And for 100 microfarad, I'll go for a this 6.3 mm 2.5 mm pitch. Dia is 6.3 to pitch is 2.5. Let me go for this. And 7805. So for 7805, let's check what is the package for 7805. So we will go 7805. Let me search LM 7805. So this is the pack, and this is the device. So the package is TO220 3-pin. So TO through hole. TO or SO, we need TO220. 220 3-pin. There is horizontal and vertical. So let's see what is this. Only 2-pin, not this one. We need this. So it is soldered here. We will not go for this. Let's use a one which is standing upright. We will do this. So we'll have to fit a heatsink for this, so that since it's a linear regulator, if you remember our power supply chapter, there will be a lot of heat generated. So we have to provide some space here for heatsink. So you can go and find out which heatsink is available in your local market and use that. If this is not available, then what we can do is so they don't have one with heatsink. So what we can do is we can draw one component, or we can draw a 7805 with heatsink. So let's do that. as an exercise. So we will not use this. We will draw a custom footprint for 7805. So to draw a custom footprint, come to the project sheet, then footprint editor. So if you come here now you have to create a footprint. Go File, New Library. So let's create a new library. Library is a group of footprints. For example, this is a connector underscore din library which has a lot of footprints. So now let's create a library first. New library, let's call it as tutorial. Do you want to available for this project or global? Global. So now we have created a tutorial. So now inside this we have to create a footprint. File, new footprint. So let's give a name 7805 with heatsink. So the best thing is not link it to a particular component. Let's link it to TO220 with heatsink. Okay, so now we have done this. Now we have to create a pin, add pad. So before that, let's open a 7805 datasheet and see what is the size. So here, let's open this datasheet. The package drawing is generally given in the last section of the datasheet. So we are going to do for a TO220. So this is the TO220. So now this is the leg. So now this we have to see what is the dia. So the dia which what is expected is between 1.22 to 1.40. The minimum is 1.22 which it can come. Maximum width of this lead can be 1.4. So let's put a 1.5, the hole size, and the gap is between two pins is from 2.29 to 2.79. So the standard is 2.54. So it's always a multiple of 2.54 or 1.27 or 5.08. So it is like mils they call it, that is in the inch system of measurement. So 2.54 is the pitch between the two leads and the hole size should be 1.5. Okay, if you come here, so this is the hole and grid will keep it to 2.54. So it's easier to place, or 100 mils, 2.54. So let's see the properties. You can double click on it or hover and press C. So here the hole size is what we want is 1.5. So and the pad size should definitely be more than 1.5 or else it will be a very thin pad. So let's make it 2 for a circular pad. So now this we can go higher, but what happens if you go 3? There is more pad. What happens is if this is 3, pin 1 and pin 2, it will get shorted. So I'll just show you. So if I let me keep this, so the next pad, if I keep it to here, these two are getting shorted. We don't want this to happen. So what we will do here is we have to reduce this, but I don't want the pad to become very small. For example, I can have this at 2, but the pad is very small compared to the hole. So when you solder, it will not solder properly. So instead of circular, what we can go is we can go for a oval or rectangle. So let's go for a oval where this is the x and this is the y. You can go for 3 or 4 depending on your choice. Let's go with 4. So now this is first one, this is second one, this is third one. Okay, now we have 3 leads. So this reference is that U1, this legend of the IC is going to come. Let's move it. So to select one, M is the shortcut. Just move your mouse over it. M is for move. Let's move it away. Okay, this hole will be there in both the layers. The pad for this will be available in both the top and the bottom. So copper, all copper layers. If you want the pad to be only on the top, that is the front copper. Bottom is back copper. So let's have it in both the layers. Okay, we have this. Now we have to draw an outline for this so that we don't keep any component in that area. Then this will be in the silk screen. So this indicates that whatever you are going to draw will come in this layer. So let's see what is the dimension. So if you see, the width is 10.16 and the thickness is not 5 mm. So 10 and 5. So if I start here, let me see here. I'll draw in the silk screen front. So it will be 5 this side. So if you see here, this distance is telling you what is the distance. 5. Then I'll come this way, 5. Go 10 this way. Yeah. So if you want a finer resolution or better accuracy, what you can change is you can change the grid to whichever unit you want. Let's go with for the heatsink, let's go with 1 mm. So now we can draw 1 mm. The grid size has become 1 mm. Okay, now the heatsink. So let's search for a heatsink. So let's select one of, see which is available in your local market, and these things are generally available, these kind of things. Let's go to this and see what are the dimensions. So the sizes, so it is 20, 15 and 10 mm. I think 10 mm is the height, 20 mm is the width. So let's start from here. So what I need is, I'll start with the center point. So I have to go 10 mm. So now my grid size is 10. So but what has happened is I have drawn this with a grid of 2.54. So this is not coming properly. Let me change to 2.54 itself, or I have to go for a lower grid. I'll go with 2.54, 100 mils. I have to go 10 on one direction because the width was 20. So you can keep an eye on this distance. 10, and this way it was what was it? It was 15, I guess. 15. So let me go 15. Distance 15, and this way will be 20. Come back, done. So this is the footprint. So we can create a 3D view. I have never done that. So you can Google for it how to create a 3D view for this. So let's keep it at this. So let me save this file. Save. So now we have created a library called tutorial, and we have created a component footprint called as TO220 with heatsinks. Now let's use this for our project. So we are here. So that would have not come here. We have to close it and open for that tutorial library to come here. Let me cancel. But don't apply and save, else what will happen is all the things which you have done here will go away. So now let's go to our schematic, and we were doing here assign PCB footprint. Yeah, let's come, let it load up. For this, let's see if our library has come here. Still not. It has come here, tutorial. So we have one here. So these are heat sink. Let's do this. So now we have assigned this one to the, click here, this is the footprint. This does not have a 3D view, but it shows the pads and the outline, the silk screen that we have done. Okay, now we have assigned footprint to all the components. So now the next procedure is to get it on the PCB. So before that, what we have to do is we have to create something called as a net list. Generate net list, power supply. Okay, so what is netlist? Netlist is the linking file between the schematic and the layout. So let me open the PCB. So there is nothing here because we have to link it to the netlist. We have to tell a load netlist. So we have to point it to the netlist. So this is our netlist that the schematic did, and we have to do update PCB. Now we have got all the components. So now let's place it and start routing. So we'll do a manual routing. So as I told you, you can go there, click on it and drag, or just move the mouse over it and click M. So and if you go back to the tab, like Alt tab, it will show you which component you have selected. So first we want our AC input, that is J4 and J2. To search, you can do Control F, J2. It will be selected. M, move it. Let's start at this point. So let's assume I am giving here. Again, you can select grid size here, whichever grid size you want. I generally draw in mm, so it is your wish. Some people draw it in mils, I draw it in mm. So this is the point where we are expecting to give 230 volts AC to the board. Then this is where I want to tap it out to the, in this connector I'll tap it out and give it to the transformer primary, and the secondary of the transformer is what we are expecting here, that is J3. This is J3. It's not aligning because it is at a grid of 1 mm. I generally do it at 0.1 mm. So we can align it properly. Okay, now we have to interconnect these two pads. So this is the router track. So you can draw it in two layers. One is the top, that is in KiCad it is called as front, or the bottom, that is the back. So now this shows it is in front copper. So if I click on this, this is the track, it is coming. So now this has to connect to this, and this has to connect to this. So what you can do here is I can go like this, and go like this. We can do like this. So before that, to delete a track, I just drawn it simply. Move your mouse over it and delete. If you want to delete a segment of the track that you have drawn, click on that segment and delete. Whole track is move over the track and delete. So now, so one more thing, instead of going like that, what we can do here is, like the simpler way of connecting will be to connect from between 2 and 1 and then go like this, rather than going one from here to here and the other from here to here. It's an easier connection. So it's always better for small things like this. You can go back to the schematic, change it here. So instead of jumping like this, I will connect from 1 to 2 and this 1 to 2. Then for it to reflect here, what you have to do is you have to create a netlist. As I told you, netlist is a link between the schematic and the layout. Generate netlist, just overwrite it, you come here and update PCB from schematic. Close. So now what has happened is I can connect these two like this. Okay, now the important thing is what should be the size of the track. So now this is called as a track generally. So what you can do here is you can do Q, track width. It is now 0.25. I can go for 1.5. Power tracks, you can go for a higher thickness. Always higher thickness will be better. So then this. So now I am drawing in the. If this is showing here, that is I am drawing in the front copper. Okay, now let me place my, again shortcut M. This is where I'll get the transformer secondary, that is what is this connector? This is a 5 volts output, so this will be on the other side. So next is I have to keep the diodes. These are the diodes. So D1 and D3 on the top. So it is up to you, like how do you want to place it. Resistor D1. So here 1 and 2 is the cathode. So 2 is the anode here. So our footprint selection was wrong. So either what we can do here is you can go here and change this or change this. So let's see which is which one we can change. Change footprint. So here they don't have an option where there is a diode where 1 is the anode and 2 is the cathode. So let's see if that is there in the schematic. So if I come here, I want 1 to be the cathode because here 1 is the cathode. This line tells it is cathode in a diode. I'm double clicking on it and reference library. I want 1 cathode. Now let's do one thing. Let's create a diode because we have already done. We have created a footprint where we have not created a schematic diode. Let's do that one also. To create a diode, come here, select on symbol editor and file new library. Let's create a new library for the schematic components. Let's create a, see if it has been created, tutorial, new symbol, symbol name, diode, reference, U is generally for IC and D is for diode. Okay. Let me move this. Move this. So So let me create a diode symbol. So we want cathode to be pin 1. So let me place a pin 1. Pin name is cathode. It's named as K. Pin number is 1. This is not required to name it as K. It will come up in the schematic. It will not look nice. So the input, let's make it as an output. Okay. Orientation down. Okay, this is 1. Next is the second pin. Pin number is 2. You can select any, I'll just make it as an input just to symbolically tell this is the direction of current. Up. Okay, that's it. I'll save. So let me save this also. I might have to reopen it so that library comes in. So now all these things I have to replace it with double click. Sometimes doesn't work. Let me do E. E is to go for the properties. Footprint is diode. So let's go to our tutorial diode. We copy this and paste it to the remaining ones also. To rotate, R is the shortcut, and move, M shortcut. You have to be in this selector tool to select it. Double clicking. We paste this. And for this also. My still footprint is the same which I had selected earlier. R to rotate. We connect a track. Again, whatever changes you make here, you have to create a netlist. And in the board, you have to import it. Okay, this is fine. Now I have this on one side. I'm really not trying to like squeeze it in as is a tutorial. And instead of creating all these components, you can download the components online which have the CAD, KiCad version. So I'll in the next when we do SMPS, we will not create a component, we download all the components offline. There is a website where you can download. I'll show you that. Then after this there is a capacitor. I think this is the input capacitor. R is to rotate. We have it like this. So you have to place it in such a way that there is, you do all these things in a minimal area. So now let me place the heat sink here and output. Okay, let's place the output here. Then we have an output capacitor. We have the LED here. And these are different layers. If you don't want any of these layers, you can deactivate it. So you can Google for all these things. Basically this is front copper, back copper. I'll just specify the important one. Then this is front silk screen, bottom silk screen. Then edge cut. Edge cut is the boundary. Okay, we have this. Okay, not try to make it any smaller than this. Let's keep it at this. It's your wish where you want to, how you want to position it. I'll just position it randomly now. The whole intention is to make the board as small as possible. Okay, now we have roughly placed all the components. Let's start routing, and we will route it with Q track with a 1 mm. So I can route now I'm doing it in the front copper. I can do it in the bottom copper also. For that I have to just press V. Sorry, F. Well, you can select here. I think V is a shortcut for that. Yeah, V. Click V. You can see it is toggling, or you can come here manually and do this. For a simple board like this, you don't have to go for a multi-layered board, because multi-layered board will be expensive, almost twice the cost. Just for showing you, I am doing here. And there is something called as fire. For example, you are coming like this in this layer. You've come here, now you cannot cross this. Let's assume you want to jump over it. So what we generally do here is, now you have come in the bottom layer, we'll put a via. Via is a way, you put a via, then go to the, putting a via is V. You now drew the remaining track in the front layer, that is the top layer. Then one more via, if required you can do, or else you can just connect it here. Okay, I'll just tell you what we did. So what we did was, we came in the green is the bottom layer, or the back layer. We came here, we came here, and we came here. We have seen that we were not able to cross this. If you want to cross it, a via is nothing but a hole. So once you put a hole, what happens is, when the PCB is fabricated, the inner surface of the hole will make a contact from the top to bottom. So what happens is, you put a hole, the electrical connection will come to the top, and from top you can finish the remaining of the routing. So this will be useful when your board gets more and more complicated, where you'll have to do, for a board like this you can just do it in single layer. Okay, now here, yes, and if you want to adjust these kind of things, like hover over it and press D. This is a very important, very useful option. D is a shortcut. So I'm not placing any of them, just randomly showing you how to do it. You can join it here. Then to this, I'll join it here. The connector, I can do this. Okay, this is, you have to practice. The more PCBs you draw, the better you'll get at it. So now I have connected all the nets. So let's now, if you see, let's see it in a file view, 3D view. So now this is the 3D view. This is how I have placed all the components. Okay. So now, so ideally, if the single layer board, like, you'll draw it in the bottom layer, because the component will come from the top, because all of them are through hole components. It'll go through the hole in the PCB, and bottom is where you solder. So you can do everything in the bottom layer. So now few things that we have left out here is, one is the board outline and the mounting holes. So I'll just make a, okay, let's put some mounting holes. Let's assume that any PCB will need some mounting holes. Let's go to the schematic and put, it has mounting holes. Mounting holes, let's assume we have 4 mounting holes. Here you can do copy C, move the mouse over it, press C, it will make a copy. Then you will have to annotate it once and give a footprint for the mounting hole. So here also we'll just search for mounting. Yeah, I'm just I've selected this filter, so I can see a lot of mounting holes. Let's put a, let's assume that we are using a 3 mm screw, and we'll put a 3.5 mm. Oh, let me go back. Click on this symbol, keywords is hole. We went for 3.5 mm hole for 1, 2, 3, all the 4 holes. Okay, now let me create a netlist. Once netlist has been created, I can come to my and import it. So I have now got 4 mounting holes. I'm not optimizing the board size, I'm just giving it for a reference. I'm doing it for the sake of understanding. So let's assume I want to keep my mounting hole here. So mounting hole, but it's better to keep with 1 mm. Kind of sits properly. And you can see where you have placed it. Double click on it. Y position is 124. You want to keep it in 124. Yeah, this is also 124. And this X position should match. X is 20. This is 20. This is 74. This is 75. So this I have to make it 75. In the bottom you can see here also where I have placed it, X75. So next we have to draw outline in edge cut. So this will tell this is the my board outline. I will go from here, close, so I'll go from here. So this I'm just giving as a understanding. I have not optimized the board. So when we do the SMPS one, I'll optimize and draw it. Okay, now we have drawn the board outline. Next, now view 3D view. Now these are the holes and this is the first PCB that we have drawn. So now if you want to optimize it, let's see what all. So first thing which I told is, if you want it to be a single layer board, draw everything in the bottom. We delete everything once. I think to save time, I'll just pause the video, draw everything and come back. Maybe I can speed it up also. Draw bottom. So I've quickly drawn everything in one layer. That is the bottom. So there is now one more thing that we have missed out here is the legends. We have to tell which connector is what. So if you come here, so we can take text and write here 230 volts input. So the text will be in front cell screen, top cell screen, and mirror should be off. So when you write something on the bottom, mirror should be on. So now mirror is off and the layer is front cell screen. Okay, I have not selected it. This text, I don't want it to be mirror and I don't want it to be in front cell screen. So it has come here. You can select the size also. 230 volts. We name it as in. Then you can copy it. Control C, Control V, copy the text. Transformer inside 230 volts to what I'll do is transformer primary. Control C, Control V. Secondary, or let's say 15 volts AC. Too big, so let's have it only transformer secondary. Then this will be your output plus 5 volts DC. It's always better. Okay, this is not coming in the correct, so I want it in. Yeah, I don't want it to be front silk, and I don't want it to be mirrored. Okay, front. You can keep it that side if they're seeing it from that side. It's your wish. So, and this plus is not required, right? Yeah. And we have to also specify which is the plus. So this will be the plus. Okay, I'll write it here on this is plus. Okay, now let's save it. View 3D. Yeah. Now the connector will be like, you know where to connect what. And this will be our first PCB design completed. Let's also do a SMPS power supply with LM2576, and there we will use all assembly components, and I will try to optimize the PCB board also. Now let's design a SMPS power supply using LM2576. I'm not going to explain the design details as I have already explained it in the power supply design chapter. Please refer to that. We take one connector, it is C to copy. So instead of 4 diodes, I'll use a bridge. Okay, now there is another thing which I have to teach you here. That is, instead of let's assume that there is no other, you don't have a component here. Then what we did was, in the earlier example, we created a diode and a schematic part for the diode, and also created a layout part for it. Or there's an easy way to do that. There is a website called as Component Search Engine, from where you can download the schematic, layout, and the 3D model. Let me open that. So for next, what I require is a bridge. So I will use a bridge. So I'm designing a 1 amp circuit. So I have to use. So using a 1 amps bridge will not work. So at least I have to use a 1.5 or 2 amps bridge. So let's search one on Mauser. So I'll filter for greater than, let me put 1.5 amps. You come here, there are lots of bridges available. Let me select, let's filter based on price also. So you will get the most commonly used bridge. So let me see. 1.5 amps or 2 amps. Okay, let me see which one is available in the component search engine where I can download the footprint. I'll select that. Let me select a 2 amps one. Once you search here, you have to log in to download that, so you can log in once. So there is a 2 amp 600 volt. Let me see if they have, yeah, it has the symbol and the footprint. It does not have a 3D model, so that should be fine. So these two are what we are going to use. So let me download it. So let me extract it here. Let me paste it into our project folder. We create a folder here. Okay. Next, what I have to do here is I have to add this to the KiCad. There is preferences and a symbol library. This is the schematic. I'll add it to the global project. If I add it here, any project I create on KiCad, it will be available. So let me go here, KiCad library, yeah, RS205L. Okay, next I have to add it to the footprint also. Component, KiCad. So it has had, now we have added both the schematic and the layout footprint. Let me get back to the schematic. It was RS. One second, the name was RS205L. RS. It is available here. So it has come here automatically. So I'll add it here. And after that, I'll use the same capacitor that I've used here. Then I'll use LM2576. I'll use an adjustable version. So in case of it is a 3.3, the output is fixed to 3.3. In case of adjustable, we can adjust it using 2 resistors. Again, check out the power supply design chapter for that. Then I will need a capacitor. Then I will need a this needs a inductor and Schottky diode. Inductor, Schottky diode. Then it needs a resistor to adjust the output voltage. So instead of using 2 fixed resistors, I will use the bottom one as pot. So we can have a variable power supply. I can tune it to whichever voltage I want. Okay, then I will need a let's put a resistor and LED. Resistor, LED. Then I will need a connector for the output. I'm not using an off-page connector, I'm just putting it here. Let me pick it up. These two are the inputs. Ground, this on off should be ground. And check out the power supply design chapter. Already gone in detail in that. This has become reversed. So here I cannot connect it like this. I connected it. If I give 1, this will become a fixed resistor. So I have to connect from 2. So this variable becomes a variable resistor, and I can adjust the output voltage. This should be given to the feedback. Okay, now our schematic is complete. So now for this, what we'll do is I'll use as much as possible SMD components. You go here. First, let's annotate. So in case of LED, so I have created a library where I put whichever I need as to be there. 0805. Then there is an inductor. For inductor, okay, before that, let me show that this one. So this has already been selected automatically since we have imported it in both the packages. Or else what you can, if it was not imported, we should go to R. Let me see what it was. RS205. Yeah, it would have come here, and I had to select it like this. Okay, now inductor. Again, you can go to Mouser, find the inductor, go to component search in the engine and download it, or else I've already shown you how to manually draw it. You can go any of these two ways. So what I have done is, with the most common components that I've used, I created my own library and I'm saving into that. So it's easier to pick it. Inductor. So this I will go for a SMD resistor. And there is some filters. If you turn on some filters, you will not be able to see anything. So be careful which one is selected. To come to R, I have SMD 0805. I prefer 0805 because it's optimal size. 1206 is kind of big and 0605 is very small. So 0805 is the one which I prefer. It is always better to have one size so that you can have some stock in your R&D lab or in your home. Resistor 0805. Pot, I have created a pot. Let me search for it. Yeah, you see a 3D view of it once. Yeah, this is the pot. Schottky diode, again I'll go here, and I have a diode. Okay, let's do one thing. Let's download a Schottky diode. So generally the one Schottky diode which I use for applications like this are 1N5822. Let me search that. So let me download this. We paste into our components. So either I can add both of them, or I can add only the layout part of it. Since I have a schematic component here, I'll just add the layout part or the footprint part of it. KiCad. Okay. So now this. Oh, I think I did not save it. Let me redo the whole thing again. Here, make sure that this apply save schematic and continues. Click when you get out, or else what will happen? It will not save anything. I'm not sure if it is saved. It is not saved. So as I mentioned, let me redo the whole thing again. For Schottky diode, I have to go here. It was, let me see if it has come here. Come here. Remove the filter. I will select this. Now I have to create a netlist. Generate netlist. Then I have to go to the layout section. That is where we did the PCB, and let me import all the components. So I have all the components here. So now let me start placing it. This is my input connector. Now this time I'll try to kind of squeeze everything in together, and I'll do a multi-layered board. This is it. Then we have a Schottky diode. We need a capacitor after this. If you click this and go to your schematic, it will show which component you have selected. This is the input capacitor. Then we have this. So now I am placing all the components on the top, that is the front copper layer as per KiCad. Then I can have an inductor. Yeah, sometimes when you're routing like high current or switch mode power supplies, you have to keep an eye on what the manufacturer is telling, how you should route it. For example, if you take LM2576, get the data sheet. If you open this, so he would have given some instruction on how you should do this. So basically what he is trying to do is test circuit and layout guidelines. As in any switch regulator, layout is very important. Rapidly switching currents associated with the wiring inductance generate a voltage transient that can cause problems. Basically, if you go through it, what he is telling is terminate all the grounds to a single point. A single point ground should be used for best result. So we have to, while drawing, I'll try to do this. So once we have this, and this is the output capacitor, and this is the pot. And also what I'll do is I'll keep couple of components on the bottom layer. I'll keep these two on the bottom layer. There is no requirement to keep it on the bottom layer, just to show you. I'm going to keep few components on the bottom layer. One is this. To switch to the bottom layer, you can do F. F is to flip layers. F. So just for the sake of showing you, I am putting these two components on the bottom layer. So ideally it would be better to keep all the components on the top layer because it's easier to solder. When you're doing machine soldering, it's a one-step process. Or else what they have to do is first they have to populate and solder the top components, then flip it and populate the bottom components. If everything is on the top, it is very easy during manufacturing. Now I have it here, so let me start routing it. So the one is not connected for some reason. I think, yeah, it has not made a connection here, the net. Okay, save, create netlist, generate netlist, and you have to import here. See, now it has made the connection. So let me flip it. Okay, and this board I'm going to use both the layers for routing. Let me do one thing. Let me keep this also in the bottom layer. Let me keep it like this, and these components I'll move it here. This I'll move it here. This is a LED. Then moving one of these resistors to the top layer. Just to flip. And this one I'll keep it on the bottom. So I'll keep it on this layer. On this, it looks a bit confusing, but both are on different layers. Just for showing you, I'm just keeping one over top of the other. You can always go and see the 3D view of how it looks. View 3D. So this is outside the boundary. That is why that has not come. So this is the top and the bottom. Let me put this into this and move this board to the and holding control, the line will come straight, or else if you start moving, it will start moving all the way. As soon as you hold control, it will be a straight line. Then I use control. If I don't use control, what happens is it starts wandering around. As soon as I hit control, it will come to one point. It will become a straight line. Okay, now let's view footprint. See, these components are on the top, and this is on the bottom side. I have a inductor and a resistor. Now let's start routing it. And now this and this has been, it's like crisscrossing. The easiest way to solve that is you can come here and kind of rotate this once. Here, create netlist, generate. So you have to do everything possible in the schematic so that your layout is easier to route. Yeah, now it has straightened. Q, wire thickness, I'll make it 1. This one I am the routing is on the bottom layer. So this one I'll Press V to change layers, and I'll route this on the top. Again, this can very easily be a single layer PCB. Just for showing you, I'm making it a 2-layer PCB. This one I'll take it in a now from this layer I cannot connect like this because both are on different layers. So what I have to do is first I have to go on the top layer, hit a via, that is V. Once you do via, then you can jump to the top layer. So the connection will come like this over this via. Via is nothing but a hole which has been plated on the inner surface, so that there will be an electrical conductivity on from the bottom to the top. And just rotate it so that the routing becomes easier. Going to the bottom component, so I'll draw it in green. And this is the output actually. Again, before routing, always see if the manufacturer has given any tips when it's a switch mode power supply or modems. If you are using like GPRS modems, always check if the manufacturer has given any suggestions of how to route it. So now we need a common ground. So all the ground should go connect there. So I will use this body as the common point. So all the ground I will come and connect it here. I cannot do it in this layer because both are in two different layers. So maybe I was drawing in the green layer, that is the bottom. I shifted to top. So as much as possible, like keep the lines thicker, because now this is going to be a 1 amps power supply. Let me see, there was a software called a Saturn PCB actually that used to show what should be the thickness of the track for your specified current. Let me just see if it is still available. So these guys had a software for that. Yeah, this is it. So you can fill this up and download it. So this will show you, this will give an idea of what should be the wire thickness, what should be the wire dia for a required current, and all these things. It's a pretty good software. So when you're starting off, you can use that. Or the best thing for you is now make power tracks as thick as possible. There's a ground here. I'll connect it to. So it is not routing because my track thickness previous time I had selected 2. With 2 it is not able to route. So you have to immediately go and change it to a lower value. With 2 it cannot route because this and this will touch if I draw at a track width of 2. This and this ground also I have to connect it here. This also I have to connect it there. So let me draw it on the other layer. So I have to switch layers to connect it to this. Now I have one here. For this I have to switch layers. I'm doing everything in a hurry. You should take your time, plan how you want to route it. It will take some bit of an experience for you to understand. Like you have to do multiple boards. Like I would have probably done like close to 200, 300 boards by now. But I'm just randomly doing it because if you want to place it, plan it, it'll take some time. Next is I have to connect. So if you want to see where all it is going, this one I have to connect it. That is the feedback. So now I have to I'm going to take a longer path. So what we can do here is come here, go on this layer, come here. Yeah, now all the tracks are routed properly. So this one is pending because this and this is a common ground, so I have not connected them. So once you complete this, you can do it. Tools, let us view in the 3D view. So now my tracks are complete. Now there is a couple more things that you can do here. One is, so now this does not have a heatsink. Remember, for that linear supply we put a heatsink. This you cannot have a heatsink because it's soldered. It's soldered onto the surface of the device. So what we can do here is we can make this track, the whole PCB as the heatsink. For that, what we call as copper core. So what you can do here is, let me change the grid to 1. So whenever you're using an IC, this will heat up and it's an assembly one. So if you want to dissipate that heat with, you cannot anyway now use an heatsink here because it's an assembly. So the general procedure is used to copper core and connect it to this. I'll show you. So what I'll do here is, it's asking which layer do you want the copper core. I'll do it in both the layers. There's in the front, the top layer, and to which net it is connected. To which net? I'm going to connect it to the ground. Why ground? Because this LM2576, this is the ground, and that is, since this pad is big, this is where all the heat is, the device will put out the heat at this point. So this point is where I want to connect the copper core. So you'll understand what I'm meaning. So let me use the full board. Then this. Yeah, now it has connected to this ground. So all the heat that LM2576 will generate will be dissipated in this full area. This will act as a heat sink. And there is an advantage to this. This will also, if it's a noisy circuit, and if you have sensitive components, that it's a noise, basically what I mean, electromagnetic noise. This will kind of act, it will absorb that noise because this is providing a lot of surface area. Then if you want to link it to the top one also, so I'll just copy, paste it, put it out once, and I have to change the layer, copper bottom, and this is a clearance. Clearance means if there's some other track that is not connected to this ground, what should be the distance between these two? So 0.5 is fine. Let me move it back here, and it is done. If you set V, or does not yet come, let me Not sure what happened. Front copper. You can see the bottom copper. So what you can do is, if you click check on this, that copper layer will go away. So it's easier to select. So it is connected to no net. I have to connect it to ground. Now just come to this layer. Let me put back this layer also. So if you press V to see the layers, you can see it is on both the layers. Now what has happened is the front layer, the top layer is connected to this, but this is not connected to the bottom layer. It is connected at very few points, like this point. So the good way to do is, you provide wires from this layer to this layer so that the heat is properly dissipated. So it will flow from the one layer to another layer. So you can randomly put it in different places. So that they are electrically and thermally very closely bound. Make sure that you don't trip it on any track. Okay. Now we have done this. Let's see the 3D view once again. 3D. Now this is what you generally see on the in all the PCBs. So this whole, the top copper and the bottom copper will act as a heat sink now. So whatever heat this LM2576 puts out will be dissipated in both the top and bottom layer. So that is one thing. Now next is, again you have to keep all the legends here. After this, so now once you have done this, you have to send it out for manufacturing. So what you have to do is, you have to generate something called as a Gerber. So you can file plot. You have to plot, and you have to tell them which all layers do you want to plot. So the output will be the Gerber. So you can plot and generate drill files. So once you do these two, the software will create a Gerber file. Once you go to, I think we are done in power supply. So it has come, all the Gerber files have come here. What you can do here is, you can create a folder called as Gerber and put it inside that also. So I've just put it here. So once you, now all these files you can send it for fabrication, and they will fabricate and give you the PCB. Then you have to procure all the components and assemble and use it. So what I'll do here is, I will create PCB for all the things that we have done. That is the SMPS, the linear power supply, the SMPS power supply. Then we did the LDR circuit. Then we did the thermistor circuit. Then we did the high voltage, low to voltage cutoff circuits. So I will schematic layout and Gerber, and I'll upload it. And what I'll also try to do here is, I will, because what happens once you send this Gerber file for printing, so it will be costly if you print a single, because there will be some setup charges, film making charges, and all these things. So it will cost you like minimum of, for a board of this size, to get one board. They will not make generally one, they will make 4 or 5. It will cost you about 2 or 3,000 rupees. So what I've decided is, I will make a PCB and put it on Amazon, and I'll give you a link. And if possible, I will also give you all the components that is required for you to assemble them. So you can just directly go to the Amazon link and order it. So I am planning to do 2 kits, one with all the instruments, the basic instruments that you will need. That is multimeter, a couple of soldering iron, lead, cutters, some wires, all these things, plus the PCB that we have developed and the components. And in the other kits, if you already have all these instruments, I will give you kit 2, where you can just buy the PCB and the components, and you can solder it out and test it. And I want to keep it open source, so I'll upload all the Gerber files and everything on GitHub or some Dropbox or somewhere, and I'll share you the link. So if you are interested, you can print it out yourself. So that's, I think I've covered everything about basics. So I'll slowly move into microcontrollers. So this will complete the basic course. So next I'll start with microcontrollers, and let's see how that goes. And I will do Bluetooth. I'll write an Android app to communicate between our microcontroller and the Android app. Then let's put a GPRS modem, send the data to the web. I will also write a web application, all the database stuff, so that whatever the hardware sent goes to the web. So I'll do a full course. So this is the end of the basics. So then next one will be the microcontroller basics. Hope you guys were able to follow the first course of basic electronics. Yeah, thank you.